Occasionally, when working in right triangles, you might be asked to solve a right triangle. And so we'll talk about what that language means, but when we are thinking about our tools with right triangles, we have trig functions to work with, the Pythagorean theorem. We have the angle sum rule, just meaning like all the angles must add to 180. And then eventually, we're going to talk about inverse trig functions as well. Okay, topic for a later point in time. Okay, but for right now, when we say solve right triangles, we're going to use that bit of language to mean find everything out about it that you can, all missing sides, all missing angles. Okay. Also, a convention that we use in setting triangles up, maybe you've encountered this in the past, it is to say that the vertices follow a specific order, mainly that the angle C has a 90-degree angle and thus opposite the hypotenuse. The other two vertices don't really matter where they are, A, B, whatever. But then the side lengths are labeled in lowercase letters directly opposite of the angles. Okay, so side little a is across from angle A, etc. Okay, so just a convention. All right, so our first example, we're going to work in a right triangle. So, okay, here we go. I draw my right triangles backwards, though. Backwards of that diagram, at least. Okay, we're going to call that a right angle, C, and then A, B. All right, so we know that side A, so that's opposite of angle A, is 10, and angle B here is 22 degrees. Okay, so in total, what do I need? I need angle A, right? So I need to know what angle A is. I need to know, let's see, this is little c and little b, so I need to know what B and I need to know what C are. Okay, so that's what I need to report for my answer. All right, angle A is going to be found by doing, 90 degrees minus 22, because again, B and A are complementary. So if you do this, you get 68 degrees. Okay, you could also use the angle sum property and do even more. So 180 degrees minus 90 degrees minus 22 degrees, you end up getting the same thing of 68 degrees. Okay, so we get angle A. Yay. Oops, not 6.8, 68. Next, let's pick, well, I don't know, let's pick C. Okay, let's try and find C next. Okay, so to find C, that's the hypotenuse, I'm going to need to use a trig function because I'm going to need an angle and a side. So I'm going to do cosine. So I'm going to do cosine of, actually I'll do this in red. Cosine of 22 degrees is equal to 10 over C. Okay, and now I don't normally work horizontally, but I'm going to have to. So I'm just going to do like an arrow over here, multiply both sides by C. So I get C times cosine of 22 degrees is equal to 10. And then the next step is going to be to divide by cosine of 22 degrees. Cosine 22 degrees. And then so I get C is equal to 10 over cosine of 22 degrees. Okay. And it doesn't say to round my answer or anything, so I'm going to leave it as 10 over cosine of 22 degrees. For simplicity right now, let's say we're going to round. If I round, I should use double, like squiggle lines for approximately. This is about 10.8. Okay, just for a point of reference. To find B then, I'll have two sides, right? I have 10 and 10.8-ish. So then I can use the Pythagorean theorem to find B, or let's say I'm feeling in a mood where I want to do a lot of trig. So to find B, I could use another trig function. So let's use 22 degrees again. And with respect to 22 degrees, B would be the opposite. And I'm going to use opposite in the 10. So that is tangent. Tangent of 22 degrees is equal to b over 10, multiply both sides by 10. So I have 10 times tangent of 22 degrees is equal to b, okay? And if you approximate this, you get about 4.0, okay? But again, if it doesn't say round or approximate, we should probably write the exact value. So I'm going to write 10 times tangent of 22 degrees. And then I'm also just going to include the 4.0. Okay, so there we go. We finished our first example. Okay, and again, just to recap, we set up a diagram labeled, and I labeled the 10 across from angle A because that was side A, and angle B with 22, and found the other bits of missing information. All right, next example. Okay, this one is optional, so if you want, you can skip this one. This will not be a part of the required material right now. Eventually, maybe. Okay, we have a right triangle. Here's C, A, and B. So side A, which is opposite angle A, is 33. Side C, which is the hypotenuse, is 65. So then in total, I need side C, I need angle A, and angle B. Okay, so I need side C, angle A, and angle B. Okay, well, let's see. I'm going to start with the side because that seems easier. If I do that, I can find sides, or side, sorry, that would be angle B. What am I talking about? Oh, goodness. Side B. So I can find side B by doing the Pythagorean theorem. So that's 65 squared is equal to 33 squared plus B squared. And simplifying that and, moving things, square rooting, etc., you get 56. So that's a nice number, huh? Okay, now I need to find the angles, right? How do I do that? Well, we're going to have to actually use inverse trigonometric functions, which is why this example is optional, because we haven't really talked about it. I just wanted to include something a little bit for fun and to show you what's coming up. So the way we start those, we would start with the normal trig function. So let's say sine of angle A. Sure, that works. Pick any trig function you want, okay? And then we're going to set up our proportions. So 33 over 65. Okay. Now I want to know what A is, so I need to undo sine. The way we do that is by doing the inverse sine. I call it arc sine sometimes, but we would do inverse sine of both sides. And sine and inverse sine would cancel out leaving angle A on the left-hand side, and then this would be sine inverse of 33 over 65. And then I can punch this in a calculator or leave it like that. Either way, just for our own sake, if we approximate, it's about 30.5 degrees. So angle A, I'm going to leave that as sine inverse of 33 over 65, which is approximately 30.5 degrees. Okay, and then for side B, all I'd have to do is do 180 degrees minus 90 degrees minus that whole mess up there, using the angle sum property. Okay, if you approximate this ends up giving you about 59.5 degrees. Okay, so again, this is optional. We haven't talked about inverse functions, but just in case you're curious, like what if you were given all sides and no angles? Well, there you go. What if you were given all angles and no sides? Well, that's a little bit more of an interesting question and maybe something for you to think about.